Assalamu alaikum. I thank you for accepting my presentation. My name is Amina NOUAL. The title of the presentation is Comparative Analysis of DC Characteristics of L-GaN in L-GaN GaN MOSFET with a single and double barrier. To abort this presentation, we have an introduction, then device structure and methodology, results, we have energy band diagram, DC characteristics, we have output transfer and transconductance characteristics, and then we have comparative study, and finally we have conclusion. Gallium nitride GaN is an excellent semiconductor material for power transistor due to its wide band gap equal to 3.4 volt and high electron saturation velocity. The use of this type of materials greatly increases the carrier density of the two-dimensional electron gas 2DAG, resulting in a very high output current. So, HEMT transistor, high electron mobility transistor, is a field effect transistor incorporating a junction between two semiconducting materials with different band gaps. The most studied component today is L-GaN GaN HEMT transistors, and it has been made in the field of high power and high frequency electronic applications due to the existence of high mobility 2DAG at the L-GaN GaN interface. This device is many useful in many applications, such as we have radar, laser diode, satellite, sensor, and terrestrial telecommunication. But, however, this device with L-GaN barrier suffered from some problems. So, L-in-N and L-in-GaN alloys have appeared as new barrier layers, where we incorporate indium in the material. In L-GaN GaN HEMT demonstrated a better performance. In this figure, we present a cross-section of conventional transistor with ternary materials and quaternary materials. We can say that the L-GaN will be as an alternative for L-GaN material because it can improve the density of 2DAG and boost to increase drain current and transconductance. In this presentation, we will propose a new structure of HEMT transistor. The first structure with a single barrier is L-GaN in L-GaN GaN MOSFET transistor, noted MOSFET1, with 0.62 micrometer gate length and the ground source drain grows on 4H6 substrate. We have chosen titan high-K dielectric as an oxide layer between the gate electrode and GaN cap layer. In this structure, we have L-GaN layer as Schottky contact layer, now doped with 20 nanometer thickness. Then, in L-GaN barrier doped layer with grand band gap. Then, GaN channel and doped layer with small band gap. The confinement of electrons is in the interface in L-GaN GaN. The second structure is L-GaN in L-GaN GaN with double barrier, doped in L-GaN second barrier layer with 4 nanometer thickness is inserted. This is the difference between the first and the second structure. So in our research, we have performed a two-dimensional simulation using Silvaco Atlas software. We have these results. First, we have energy band diagram. The figure shows the conduction bands in the MOSFET under the gate electrode. The quantum well is well present at the interface between the two materials in L-GaN and the GaN channel. The conduction band profile shows a small difference between the single and double barrier in argon nitride. From the simulation, the value of the electron density of the 2-DAG gas of our MOSHEMT is about 4.85062 times 10 power 13 centimeter power minus 2. MOSHEMT for it's nearly for both structures. Second type of results is DC or static characteristics. First, we have output characteristics. In figure 5, the figure 5 presents the drain current EDS versus drain source voltage VDS of both transistors with single barrier and double barrier for different values of gate source voltage. Throughout these results, we can distinguish two zones: a nomic zone for which EDS is proportional to VDS, and the saturation zone for which the EDS current is quasi-independent of the VDS voltage. From this figure, it's noted that the current density of MOSHEMT1 is higher than that of the MOSHEMT2 transistor, which demonstrate that this transistor is suitable for high power and high frequency applications. Second, we have transfer characteristics defined by threshold voltage. Figure 6 presents the drain current EDS versus gate source voltage VGS. The extraction of the VTH is obtained by extrapolation of the transfer characteristics at EDS equals 0. The value of VTH is greater than 0, so the operating mode of the transistor is enrichment mode or E mode. Then we have transconductance characteristics shown in figure 7 is calculated from the derivative of EDS VGS curves at fixed VDS. The peak extrinsic transconductance was 635 millisiemens and 664 millisiemens at VDS equals 6 volt for single and double barrier MOSHEMT, respectively. This table presents a comparative study of the main electrical characteristics of the two transistors studied with those published. We note that MOSHEMT2 has a value of EDS maximum and transconductance max greater than that of MOSHEMT1, and from that published recently. This result makes these two transistors better candidate for power and microwave application. After studying single and double barrier MOSHEMT transistor, it's observed that the double barrier MOSHEMT transistor has an excellent DC and RF performance. We conclude that the double barrier GaN MOSHEMT transistor can be a promising candidate for high power and high frequency application. I thank you. And finally, I thank you for your attention. Thank you.